Now we shall see the next result. In closed sets, we shall see the next result. If E is any subset, if E is any subset of a metric space M, then E bar is closed. That is, the closure of the set E itself is a closed set. We have to prove it. That is, the closure of the set itself is a closed set. That is, we have to prove this one. The closure of the set itself is closed. So when we say that a set E is closed, we have to show that, we want to prove that a set E is closed, we have to show that the given set E must contain all its limit points. Now we have to show that the E bar is closed. That is, the closure of a set is a closed set. So what we have to show that is, this closure must contain its limit points. So we have to prove this one now. In this result, we have to prove this. So to prove that closure of a set is closed, that is, we have to prove this. We have to prove both the ways. See, first we have to show that E bar closure is subset of E, this one, and then we have to prove that E double bar is a subset of. But this is always true. This is always true. So now we need to prove that the closure of the set is also a closed set. This is what we have to prove. But any set and its closure, what is the relationship we have? Always the given set is a subset of its closure. This is true always. This is by a theorem. You have to cite the theorem here. Therefore, we need to show that the closure of E bar is a subset of E. This is what we have to prove. That is, if X belongs to this set, we need to show that the same X belongs to E bar. So this is what we have to prove. Finally, we have to prove this. So now we are going to assume that if X is element of E double bar. So now X is element of E double bar. This implies that any open ball, say B with center at X, contains a point of E. See, already we discussed this result. The last session we discussed this one. That is, the point X element of M is a limit point. It's a limit point of E if and only if any open ball B of x colon r with center at x contains at least one point of the set E. This is a result already proved. So now x is element of the closure of E bar, that is E double bar. So we are using this result. So implies any open ball B of with center at x and radius r contains a point of E bar. That point I will name it as y. So it contains a point y of E bar. Let us assume that S is equals to the distance between x and y. And clearly S must be less than R because see this point y, suppose this is an open ball whose center is at x and radius is r, and we just now showed that this y is inside this y is inside this open ball. So this radius is s we have taken. So this distance between x and y must be less than the radius, otherwise it will be outside this open ball. So that's why s is less than r. It's very clear. So we assume that s is equal to the distance between x and y. Now since s and r are not equal, so now I am going to choose another variable. Choose a real number t which is positive number such that t is less than r minus s. Here r so definitely r minus s is greater than 0. So like this one variable we are assuming t equals to, but t must be positive, but anyway this is positive, so t must be positive. So we assume that t is greater than 0 such that t is less than r minus s. Now we are going to use this result now. So what we have assumed here just now proved that this a point y bar of E, this y is belonging to the closure of E, that is E bar. Now that result, this part I am going to explain now. Since this y is an element of the closure of E, see how will you read this one is closure of E. So again I am going to use the same result, this result. The same result we are going to use it here now. That is a general result. Now y is element of the closure of E, that is y is the limit point of E, that is the meaning of this. This is nothing but y is a limit point of E. Here x is element of the E double closure means the meaning is x is a limit point of E bar. That's all. So to avoid confusion you can understand like this also. Now y is the limit point of E. So what is this statement says? This implies that so the open ball, any open ball whose center is at what? Y. I am going to assume the radius is this one. That's why we create this new variable. Right? This open ball contains a point of what? See, y is element of the limit point of E. So according to this theorem, this open ball should contain a point of E. To show the which is the point, that arbitrary point, I am going to put it as the point. I will put, already we used x, y, so now z, point z of E. Therefore, so this point z is inside this open ball. So what will happen? You construct this open ball whose center is y, radius is t. We have just now shown that this point z, which belongs to E, is inside this open ball here. This open ball contains a point z of E. So what is this distance? So you have to think. Therefore, the distance between y and z is definitely less than t. because that is the radius of the open ball. So what is T we have assumed? T is still less than what? R minus S, or we can use it as R minus S, T equal to R minus S also. Okay, so now rho, the distance between Y and Z is less than R minus S. See, it's less than R minus S. Therefore, so now we are going to use a triangle inequality. What is the distance between X and Z is less than or equal to distance between X and Y plus distance between Y and Z. But what is the distance between X and Y? Is equals to S. Is equals to S. And what about the distance between Y and Z? That is less than R minus S. So we have to put the symbol less than R minus S. But what is the final answer? It is the distance between X and Z is less than R, which implies, what you can tell about this Z? See, whenever the distance between any two elements, distance between X and any other element is, just a second, yes, see here, this S is what? Less than R. So this is the open ball we are going to concentrate now. So what, from this one and this open ball you have to see now. So what happens is, the distance between the center of this open ball, that is X, and some other variable is what? Less than R. So what you can tell about this? This Z is an element of the open ball B of, this is a final conclusion. That is, but this is any open ball. This is a general open ball with center at X. So what? So from this, what we can get is, this implies that the same theorem we are going to use it. This is a if and only if statement. This is a if and only if statement. So any open ball B contains a point of E, then that point is a limit point of E. So Z is element of B of X colon R. This implies that this open ball B of X colon R contains a point Z of E. So this contains a point Z of E. So what you can tell from this statement? See here, this is an if and only if statement. Both ways it is true. So just now we shown that any open ball of this type, B of X with center at X and radius is R, contains a point of E. So if this is satisfied, so what is happening? That center point of that open ball is the limit point of E. So therefore, from the same theorem we get that X is a limit point of E. X is a limit point of E means what? That is, X is element of E bar. So now what we assumed in the beginning, X is element of E double bar. Finally what we proved? X is element of E bar. Therefore E double bar is a subset of E bar. Therefore already the other way is true always. So therefore the closure of the set E is always closed. That is, closure of a set is a closed set. Okay, so this is what we come to the final. Little bit confusing, but if we learn many times, that you can understand why we take in between suddenly a new variable t, that is less than r minus s. Everything you will come to know. So this theorem is the main one. So this is a theorem we used many times inside this theorem, but it is not in the same variables. but each time that set will be changed. Okay, so this is the main theorem we use. And here, see, from this step to this step, we use that theorem. I will highlight this. This theorem we have used it. That's why we got this implication here. This implies this is a limit point of view. And also, yes, this also, this implication also, we use the theorem. What theorem is? This shaded one, this one, this result. Because X is a limit point of view, then any open ball, we use the other way. The necessary and sufficient, but both the things we used in this theorem. See, the same theorem, we used that any open ball B contains a point Y of. And again here also, see. The sets are only changed, but the same statement we used 3 times. First here, then in the final stage. Okay. So this completes the proof of the theorem.